I understand this current density. Current density is an vector function. The
Like you have the choice to upload or not beforehand, but if I do that, it's by March 1st anyway, so I plan on having them all finished.
So will you be talking right there? Is it live or is it recorded?
It's live.
But you're saying there is an option to upload it beforehand.
Yeah, I guess so. People can look at it and see the question.
Yeah. So is all of us here? Oh, Bowden is quitting us, I guess.
Yeah. I got pretty busy earlier, so I didn't have time to make it to class.
Sure. Yeah. Let's say some advantages of our online. Okay, let me set this up. So those who were there last class, I think Jeremy and Matt, I think, where's Matt? Let Matt. So we got disconnected last time, correct? Jeremy? Yeah. So I think it was an internet issue on our end. It was not your problem. So I thought I will quickly do that part and then go ahead. I think that's, even though we worked on it a little afterwards. Yeah, Curtis, you were also there, right? Last.
Oh yeah.
Yeah, you know, you never miss. But you're very quiet always. Okay. Remind me where I was. I realized that we missed that something only when I reached here. So I was prepared for going ahead. Did we? Let me summarize it. It doesn't matter. So first of all, homework. Homework 4 is due on March 1. It's Monday. And midterm 2 is due March 20th. Well, probably again take home. We'll see. I haven't graded your exam yet. So after that, I'll decide what's the nature of midterm 2. Anything else in general? Anything you want to say? Point out. Okay, so I don't remember exactly where we were. So we were working out the magnetic potential due to a circular wire of in the far field approximation, right? Approximation. And we said, so that's your circular wire. And there is a region, somewhere there's an observation point, that's your A. And in cylindrical coordinates, that will be your Z, and that's your rho, right? So we wanted to talk about situations when A is significantly small compared to rho, A is significantly small compared to Z, and of course, if it's small compared to both, then of course A will be very much less than R also, right? So it's an implication. And let's also use the angle theta here. We will see it plays a role later on. So the current density for this current carrying wire is, it's in the direction of, it's in the tangential direction, the cylindrical coordinate tangential direction. That's phi prime. There's a current I going through it, and there is radius is fixed to A. That's using the delta function, and radius is with prime, right? And Z prime is set to 0. The magnetic potential, it's A of R, observation point is basically add up all the sources everywhere around, right? So this is the Q bar, so add up, right? This is superposition principle. Add up all the regions where there are currents, which is only on this wire. And from each point, there is a, how much contribution does it get is decided by how far that is from the current source. So that's how far is the observation point from the current source at a certain point R prime. This we said was equal to dz prime, rho prime, d rho prime, d phi prime, 0 to 2 pi, 0 to infinity, minus infinity to plus infinity, phi prime, and we had rho prime minus a, z prime is to be set to 0, and this was basically z minus z prime square plus rho square plus rho prime square minus 2 rho prime cosine of phi minus phi prime. And square root of that. When I set z prime equal to 0, this goes away. Rho prime equal to a, this rho primes get replaced with a, and that leads to mu naught over 4 pi times z prime integral is gone, rho prime integral is gone due to the delta function properties. That is a, and there's an I also. A times I, and I have 0 to 2 pi d phi prime, and that is just phi prime in the numerator divided by z square plus rho square plus a square minus 2a rho times cosine of phi minus phi prime. Again, just repeating, but that doesn't hurt to go over this a little bit. Z square plus rho square in the geometry there is, am I still in the, you guys missed the line, I guess. Sorry. So I was basically replacing z prime to 0, rho prime to a, and you get the simplification that delta functions are gone, the integrals are gone, and rho prime gets an a there. That's what it is. This z square plus rho square is nothing but, if you look at the geometry there, the right angle geometry, rho z plus r square. So this is nothing but r square. That's a small simplification. And if I were to pull this r square out, and r really doesn't depend on the angle phi, right? That's an observation point from the origin. That distance doesn't change when I change the phi prime, which is basically on the circle. Right? Where I am doesn't matter. The origin and the observation point are independent of the source point. So it's mu naught over 4 pi a times I over r, right? So I'm pulling this out of the square root, but then I can also pull it out of the integral because r is independent on that. So that's 0 to 2 pi d phi prime, that's phi prime. After I pull that out, that stays 1. Right? Once I pull that out, that becomes 1. This becomes plus a square over r square. Since I pulled out an r, I have to divide the rest by r. So that's minus 2 times a over r times rho over r and cosine of phi minus phi prime. Okay. Now the point is, a I said is very much smaller than r. So a is very much smaller than r means that a over r is very much less than 1, not just less than 1, it is very much less than 1. So if it is 10% accuracy, you would say this is 0.1. If this is 0.1, the square of that will be 0.01. Right? So this is significantly smaller than this. One might worry that, oh, maybe the coefficients make it bigger, but then coefficient is always less than 1. Rho is always less than r, and cosine is always less than 1. So that doesn't affect it. So this is a much more smaller quantity than the third term. The third term is bigger than the second term. So in that, the far field approximation involves neglecting this relative to this term. Right? Basically, as far as you're not 0, keep the leading term. That's the point. See, if we have already neglected this, there is a square root here, use a binomial expansion to expand it. And so for example, 1 over 1 minus x, square root of this is equal to 1 plus 1 by 2x. Plus there are higher terms, that is x squared. But anyway, I have decided to drop the x squared. So even don't keep this term. So this square root quantity can be expanded in terms of this as 1 by 2 of this whole thing will act like x. Any questions there? Okay. I think we surely did all this. This is mu naught over 4 pi ai over r and 0 to 2 pi d phi prime, and that is phi prime hat, and the square root quantity is 1. This is minus x, so it is plus half, right? So that I'm taking care of that minus sign. So that's plus half times 2 times a over r times rho over r times cosine of phi minus phi prime. There are of course higher terms, but we are not keeping them, right? That's the far field approximation. The far field approximation involves that you keep only this term. So that's the first term here is an integral of the tangential vector all over the current carrying wire, but d phi prime hat 0 to 2 pi. Notice this is a circle, and the tangent vector will be like this everywhere on the circle, And if you were to add all these vectors for every vector, tangent vector, right across the diameter, there is another one which is pointing in the opposite direction. And since these are vector additions, they all cancel out. That's equal to 0. And we did this before. That is how we argued that, oh, if you want it on the axis, actually that's the same approximation, and that really comes out to be 0. So we used that fact, or we came across that fact before. So the second term is what dominates, and the second term, notice A over R doesn't depend on phi prime. The only quantity that depends is this cosine phi prime. So we can pull out all these quantities, and let's write that as so the vector potential A of R is equal to mu naught over 4 pi A times I over R, and A over R and rho over R come out because they are independent of phi prime, and what is remaining is 0 to 2 pi d phi prime, and that is a tangent vector. So this is a vector addition we are doing all over the circle, but not just the vector addition, it is multiplied by cosine phi minus phi prime. So there's a chance that it could contribute. Okay. So any questions at this stage? Right. And we did cross this, right? I exactly don't remember where, yeah, but I can do that integral. Okay, so let's do that integral alone. So 0 to 2 pi d phi prime hat cosine of phi minus phi prime is equal to d phi prime. Phi prime, remember, is minus sine phi prime. And in the I hat direction plus cosine phi prime in the j hat direction. There might be simpler ways of easier way of doing this, but let's just do it bluntly without worrying about shortcuts. So that's equal to, these are two integrals basically, and each of this cosine phi can be expanded out. So let me write this as 0 to 2 pi d phi prime, and this is minus sine phi prime, and there is a cosine phi prime. So it's cosine phi prime in the I hat direction. And the next term is minus, right? So it's a minus becomes plus, so it's plus and a minus again. So it's minus sine phi prime, sine phi prime. Right, that's I hat. That's the second term. I'm expanding the cosine plus cosine phi prime, cosine phi prime, I hat direction plus sine phi. Okay. Let me collect certain terms. Notice that there is a cosine. Let me collect which terms. Oh yeah. Okay, that's j hat. Yeah, so let me write it in the following way. That should be in the range. Okay. That's equal to cosine phi can come out. That's minus cosine phi times I hat, and I have 0 to 2 pi d phi prime sine phi prime cosine phi prime. That's one integral. The next one is minus sine phi I hat and 0 to 2 pi d phi prime sine square phi prime. Then I have plus cosine phi j hat 0 to 2 pi d phi prime cosine square phi prime. And finally, plus 0 to 2 pi d phi prime sine phi prime cosine phi prime. Just expanding with blunt algebra there. These two, the product of sine and cosine makes it a sine of a double angle, sine 2 phi. This is sine of 2 phi prime. And sine of 2 phi prime, if you go from 0 to 2 pi, basically sine of phi is like this, that's 0 to pi. If you had to do sine of 2 phi, it goes 2 times. Right? That's all it does. But still it is periodic, so this will always cancel this. So that's equal to 0. So this goes to 0, and that also goes to 0. So we are left out with cosine square phi prime and sine square phi prime. Cosine square phi prime, the integral is, or you can think of this as cosine square phi prime is 1 plus cosine of 2 phi prime over 2. But then the second term again is periodic, so that's equal to 0. And this one is 1 minus cosine 2 phi prime over 2. So the plus or minus term anyway goes to 0. So it's the half factor of half that contributes. So the factor of half contributes as cosine of phi j hat. Oh, something is wrong here. No, it's okay. It's okay. Yeah, this goes to 0, so I have. Yeah. So that's the same as half integral 0 to 2 pi. That's just basically pi. So there's a 2 pi and divided by 2. So that makes it a pi. And there's a minus sine phi I hat and again a pi. So that's equal to pi times minus sine phi I hat plus cosine phi j hat. Did we do this last time? Jeremy, were you there until here?
It cut out like when you on the left side of the board. That's basically whenever it stopped. So we didn't,
So this was not done.
no.
Oh, so then I should go slow. Okay.
Not this time.
Yeah, well, I was going fast because I thought, okay, this is repetition. Okay. Yeah, so I think each of this integral is straightforward after you expand, that is sine phi, cosine phi prime, sine square phi prime. Each of this integral is straightforward, but I sort of gave a hint as to what it is, and it comes out to be this quantity here. But this should ring a bell. This is nothing but we started with a phi prime tangent vector, but this is a tangent vector with respect to the observation point phi. So it's a very similar quantity. So that's phi hat. So basically what we have shown is that the integral 0 to 2 pi of all the tangent vectors on the wire, the source tangent vectors, when you take the component of that, or not component, if you were to actually scale it with cosine of phi minus phi prime for each quantity, this has the simple feature that this is simply phi hat, which is related to the observation point, right? So add up all the sources and gives you the direction of the observation. So that's reasonably simple. So we can actually put it back in our vector potential, and we have a closed form expression for the vector potential. But now we want to process that. So what we have is vector potential A is equal to mu naught over 4 pi times there was a current I, that is A over R, there were two of them, so it's A square over R square, and then there is a rho over R, and that is F pi hat. That's here. Oh, and then there is a pi also, right? There's a pi. Okay, that's what we have. And remember our geometry here. That's your loop. That's your z hat direction if you want. That's your vector R. And if you want, this is rho. That's your z, and that's your A. Right. Notice the area of that loop is pi a square. And if I multiply that area with the current going through the wire, I get the quantity called the magnetic dipole moment. And the magnitude of the dipole moment of the area of the current carrying loop. A loop of wire has a surface. What is its direction? It is perpendicular to the loop, and the sense of current in the wire actually gives you the direction to be in the upward direction. So that's if you talk about the vector magnetic moment, that's I times pi a square, which is area, times z hat. That's your magnetic dipole moment. So it seems like there is this m sitting in here, right? So let me put that in. So this seems like it is mu naught over 4 pi times m times rho, right, over r cubed. And there is a phi. Correct. Let's go back to our, spherical coordinates. Notice I introduced the angle theta here. If this is theta, then rho is actually r sine theta. So that's the same as mu over 4 pi times m times r times sine theta over r cubed times pi hat. M times r times sine theta sort of gives you a hint that maybe there is a cross product in here. Maybe that's an indication at least. And it is indeed a cross product. So let's look at m crossed with r, vector r. The cross product of a quantity is the magnitude m times the magnitude of the second vector, and its direction is given in terms of r. Magnitude is given as a sine theta also, right? Angle between the two vectors, and this is z crossed with r hat, but so the right hand rule, right? So z crossed with r hat, that's going into the board, and you recognize that that's also phi hat. Is that clear? Is that absolutely clear, or should I clarify more on that? You can also think of it, if you want to look at it in another way. This is also M cross R, right? Replace it with, I don't know whether this is easier at all or not. So R can be written in terms of rho hat plus Z hat, right? How much in the rho hat direction? So that's R sine theta, right? So R sine theta, that's your rho if you want, and Z times Z hat. So that's the same as M times R sine theta times Z crossed with rho hat plus M times Z times Z cross Z. But Z cross Z is 0, Z crossed with rho hat is much more clear, so that's phi hat for sure. And in case you ever read that away, how did this phi hat show? Okay, did I cross that? Okay, so all that tells us that there is a neat little simple expression for the magnetic vector potential, and that is mu naught over 4 pi times M crossed with R over R cubed. And of course, its direction is in the phi hat direction. So everywhere it first of all dies off as 1 over R square actually, because there's an R in the numerator, and its direction is given in terms of the cross product between M and R. Remember M, so what we have is M is in this direction, so that's your loop, that's your M, and that's your R. And cross product M cross R gives you the direction of A, which is circular, right? So this will always be. So A is like this. And it keeps dying off as you go farther and farther, but it is basically circular. Pretty much tangential to the circular wire all the time. But this is also a magnet, so magnetic field should be similar to a magnet, right? Magnetic field lines are very familiar. How do you get the magnetic field line? So let's do that. So B should be del cross A. Now that we have A, it's exact in the sense that we are in the far field approximation. So as far as you're relatively far, so that's exact. So what is this equal to? Maybe I should go to the other side of the board. So B is equal to del crossed with, you have M crossed with, so these are 3 vectors now, R over R cubed. I wrote it in a certain way so that the third quantity can be imagined to be a single vector. Use the back-cab rule, but this time back-cab should be used with the idea that this is a gradient operator. As a gradient operator distributes into 2, the back-cab rule, the vector operation also distributes into 2. So in principle, there are 4 terms, but M is a constant as far as the gradient goes, so that doesn't get operated. So this comes out to be equal to M times the gradient, divergence of R over R cubed. So this has to act on both, right? So this is a dot product, but the gradient has to act on that. And the second operation is when the third vector is getting the vector direction, but then M doesn't depend on the gradients or the spatial coordinates, so I can bring it out and write it in this form. Still, the gradient has to act on it. So So that's a different notice. This is a divergence. This is not a divergence. This is a directional derivative. If you So if I can get this operation straight, I can actually get this by taking the dot product of that quantity. So we have done this a few number of times in the first semester, but let's do this. So that's your, so no operation in between. Notice two vectors, no operation. So in a sense, that is a dyadic. So distribution property, either it acts on the first numerator or the denominator. When it acts on the numerator, that's this, and the denominator stays intact, or it hits the denominator and the numerator stays intact. Notice no vector operation in between, so it's a dyadic in that sense. This we said was 1, right? That's the information we were using. This is 1. That's a unit dyadic if you want. R cube. And when you differentiate this, this gives you a -3 over r raised to 4. And then you have to hit the gradient of that. The gradient of r. That's the magnitude of r, notice. And this is vector r. But the gradient operation of the magnitude of the position r is nothing but r hat. So this is the same as the unit dyadic over r cube. One of the r's I can kill from here, so that's -3 times vector r hat over r cube. Notice no vector operation again. If there was a dot product, that will go away. Okay. Using these quantities, actually now I can do the dot product also. Because the first expression had this. That means I have to take the trace of this dyadic, so that's 3. Right? So dot means the trace of the dyadic, so that's 3 over r cube minus, when I take the dot of the two vectors here, that's 1 minus 3 over r cube, which is exactly 0. But one might worry that, oh, what happens when r equal to 0? But remember, r is very much greater than a, right? Which is greater than 0. So r is never 0. In the far field approximation, we never come close by. So we are reasonably safe there. But we can always say this is a point dipole, and maybe we can actually come closer and closer, and we'll talk about that later. So this is surely okay when r is not equal to 0. Right? But one might wonder what happens when r is equal to 0, which we'll come back and do that on Friday. But using these quantities, what's our magnetic field? Magnetic field now is, substitute this back in there. So the first term is 0 minus of m dotted with this quantity, so it's 1 over r cube minus 3 vector r hat over r cube. That's the same as m dotted with r, so this is 1 over r cube. Very similar expression to the electric dipole, almost identical, except that electric dipole was P or D there, and here it is different. This is m dotted with r hat and hat minus m. Everywhere except r not equal to 0. Except when r is equal to 0. How does this look like? We have tried to draw this in the first semester, but this looks like, so if this is your dipole moment, it doesn't have to be along the z-axis, but if we choose this to be the z-axis, this looks like this. Magnetic field looks like this, which we know is a familiar magnetic fields due to dipoles. Right? Sorry, magnetic field due to the magnet, bar magnet. And this is, of course, three-dimensional, and that's easy. In principle, you should be able to calculate at any given point what's the magnetic field. If I give you the position R, so remember that's your R. That's somewhere here. If I give you the R, then if M is in the Z direction, you can exactly know what your magnetic field is. It's very clear that everywhere on this plane, it is pointing downward. Everywhere along the axis, it is pointing upward. Everywhere else, there will be a component acting in given by those field lines. Next time, we will come and verify. Like, remember, we had some identities here. Like when we were working, we made sure that the Lorentz gauge should be satisfied, and del cross A we already checked is equal to B. And more importantly, we should make sure that the divergence of B is 0. And here, since R is not equal to 0, was used, so it's not very obvious. So we would like to check that, and we will do that next time. So for now, I think I will stop here, even though it's before time. Any questions as such?
See you around.
Okay, good. Bowden, you good?
Yes.
Okay. Okay, have a nice day.
Yeah, sorry, I was just finishing writing some stuff.
Finishing what?
I was just finishing writing down.
Oh, sure. Yeah, I will keep it.
Okay. We didn't have a quiz today, right?
Oh, I forgot again. Yeah, no quiz. Yeah, I think it's too late to.
Okay.
Yeah.
All right. I'll see you on Friday then.
Okay, bye. Bye.